Next topic is next topic is diagonalizable operator. This is new definition. Diagonalizable operator. It says that a linear operator phi from V to V is said to be diagonalizable operator. Said to be diagonalizable operator if we can find if we can find or we can say if there exists on the same thing a basis we can find a basis of V for which with respect to which matrix representation of phi is a diagonal matrix, for which or with respect to which matrix representation of phi is a diagonal matrix. What I am trying to say is you have this capital V, this is phi. We want to make a definition for diagonalizable operator. It says that we know that there are many bases, rather infinitely many bases for a vector space, and it says that there is some particular basis B with respect to which when we represent this capital B in matrix form, this matrix representation of phi with respect to this B is a diagonal matrix if we can find, again the thing remains the same, if we can find such basis, then we say that the matrix is diagonalizable. We cannot find, if we are not able to find, then we say that the operator is not diagonalizable. Okay, so obviously if no such basis capital B exists, then we say that phi is not diagonalizable. Fine, clear to everyone. Now a theorem exists which says that when a matrix will be when a linear operator will be diagonalizable, then under which circumstances it will be diagonalizable. Okay, so you say a linear operator is diagonal. This is theorem. It says that a linear operator phi from V to V, or you can simply say phi belong to home VV. Okay, or you simply say phi belong to LV. Okay, on the same thing, you can simply say this is a linear operator from V to V, or you can say that this is element of home VV, or you can say this is element of LV. Both represent the same thing. A linear operator is diagonalizable a linear operator is diagonalizable if and only if there exists a basis of capital V containing eigenvectors of capital phi. This is a very, very important theorem in the sense that this theorem will become lemma for most of the theorems of diagonalization for linear operators. Okay, so theorem is very simple. It says that let proof is, this is proof obviously, let phi from V to V is diagonalizable linear operator. Let phi from V to V is diagonalizable linear operator. Then by definition there exists then by definition there exists a basis say B is equal to V1, V2 up to so on Vn. Then there exists a basis V1, V2 up to Vn with respect to which cap phi B is a diagonal matrix. I hope this is clear to everyone, with which it is a diagonal matrix. So you know that, okay, let phi B is, let phi B is, this is a diagonal matrix, and I say that, for example, this is 1 0 0 up to so on 0 a to 0 up to so on up to so on up to so on 0 0 up to so on a n. And you know that a1 ai belong to f for all I. You know this. So this is your definition. Now, if you remember, we did this in the first lecture, prerequisite. We said how this matrix is formed. You know that this matrix is formed by how the matrix representation of a linear operator is formed. You should understand this. You have this basis, you have this linear operator, you have this vectors, these vector spaces. You take element from this side, find its image. When you will find image, you will be having element on right hand side. This vector space is also having basis. Since it has basis, element of vector space can be written as a linear combination of, can be written as linear combination of these vectors. When you represent them as linear combination of vectors, then you will get the thing. Now from this we want to see one thing is, you take basis, find the linear combinations, then make the matrix. Other is you have matrix and now write the linear representations or linear combination. So you see that this matrix is formed when I take first vector v1 from this basis. I take first vector v1 from this basis, and when I take this vector, whatever the image of this vector with respect to phi 1 will give first column of this matrix. Okay, so it is a1 v1 0 into v2 up to so on 0 into vn. I hope this is clear to you. Then phi v2 is 0 into v1 a into v2 up to so on 0 into v. Then you have v3 0 into v1 0 into v2 a3 into v3 up to so on 0 into vn. Then up to so on 5v, and you have 0 v1 up to so on a and vn. IE, what is IE? IE is phi v1 is equal to lambda 1 v1, comma phi v2 is equal to lambda 2 v2 up to so on phi vn is equal to lambda n vn. I think this thing is clear to you. So you say that you have v to v, phi from v to v you have. When you have phi from v to v, you have this matrix, okay. And when you start finding the images of basis elements with respect to phi, you observe that I should have written a1, a2 up to so on an. Therefore a1, a2 up to so on an are eigenvalues of capital phi with respect to, with eigenvectors v1, v2 up to so on vn respectively. Therefore, so when you started this thing, you said that this is a basis of capital V. Now you are saying that this is vector space capital V. At the same time, these vectors v1, v2 up to vn are also becoming are also becoming eigenvectors of of phi. So this means that hence what hence is B is basis containing containing eigenvectors of phi. So first part is you take phi to be diagonalizable. Since it is diagonalizable, therefore by definition basis exists. When basis exists, you check those elements of basis becomes eigenvectors of phi. Therefore, you say that you have basis of capital V, but those elements of basis are at the same time working as basis also. At the same time, they are eigenvectors of phi also. I hope this thing is clear to everyone. Okay. Now, converse part. Converse part is converse part is you say given phi has a basis which consists of which consists of which consists of eigenvectors of phi. Okay, now you say that let lambda 1, lambda 2 up to so on lambda n be eigenvalues of phi, and v1 v2 up to so on vn be corresponding eigenvectors then by statement means this thing. Okay, then by statement v1 v2 up to vn is basis of is basis of is basis of phi, because you say that phi has a basis, okay, which contains eigenvectors of phi. This means when you take eigenvectors of phi, you will combine them, it will become basis of vector space. I think this much is clear to everyone. Now I should have written phi vi is equal to lambda I vi for all I here, so I made space for this. Now you say that you have a basis. Whenever you have a basis, what you say? You say phi v1, phi v2 up to so on phi vn. This is lambda 1 v1 plus 0 v2 plus up to so on 0 vn. What I am trying to do is I am trying to write the images as a linear combination of basis element. When I will write them as linear combination of basis element, then I will write the matrix representation of a linear operator with respect to the basis. So first thing gives first column lambda 1 0 0 up to so on 0. Second is v2. This is lambda 2 v2. You know this. So you write 0 v1 plus up to so on 0 vn. So you say this will give second column. In the same way, you will be having last column. So this is lambda vn. I hope this is clear. So you have this thing. Hence phi is diagonalizable. So if you observe, you will find that this theorem and this theorem, obviously this part and this part, they are just reciprocal of each other. If you simply start from this and start moving upward, you will be writing this thing. This is clear to you, okay? So this is a very, very important theorem. In the form of lemma, it will appear, okay? I hope it is clear to everyone. Now using this this lemma, using this lemma, we will do some numericals. Okay. Now the question is how to do the numerical part. First thing is, when a linear operator is given, we want to find eigenvalues, eigenvector, diagonalization, so and so and so. The most important thing is, whenever a linear operator is given, our first step is, our first work is to convert that linear operator into a matrix. You know this. So what I am trying to say is, whenever a question of linear operator appears to you, you simply think that even if a linear operator is given, I will convert it into a matrix. So questions for linear operators and matrix are actually the same. The only thing is, when you are given a linear operator, then your first step is to convert it into a matrix. Otherwise, all other things remain the same. For example, first question is phi of x y z. This is 3x plus y plus 4z comma 2y plus 6z comma 5z. This is given to you. Now, when a linear operator is given, step 1, find matrix representation. Find matrix representation. Step 2, characteristic equation, eigenvalues. Okay, when you find eigenvalues, I am writing this. Eigenvalues will be 3 to 5. So you say all eigenvalues are distinct. If all eigenvalues are distinct, then you know that the matrix is diagonalizable. If the matrix is diagonalizable, then obviously the linear operator is also diagonalizable. See, there is no difference between matrix and linear operator. They represent the same thing. Okay. So when you find the when you find the eigenvalues, you have these three eigenvalues. You say, since all eigenvalues are distinct, therefore LO is diagonalizable. First, see, the question can appear in two ways, you know this. Either they say that whether it is diagonalizable or not, say yes or no, 2 marks question. Second question is whether it is diagonalizable or not, tell and also find the, okay. In matrices, they say find matrix P so that P inverse AP is a diagonal matrix. Here the definition is a bit different. In this definition of for linear operators, you know, in this definition they say find basis for which the matrix become a diagonal matrix. Okay. So in this, when you have a question of linear operator, you will not find matrix P. Question will remain the same. Find matrix, then find eigenvalues, then find eigenvectors, then do not make P. Instead, with these eigenvectors, make basis. Make basis. Okay. So a question is given in which they say, question is, second question is, in this second question they say, and I again request you to do these numericals. Phi of x, y, z. This is equal to 7x plus 4y minus z, 4x plus 7y minus z, and minus 4x minus 4y minus 4z. This thing is given. You find, first step, you find matrix. Second step, characteristic equation. Third step, eigenvalues. When you find eigenvalues, eigenvalues are 3, 3 and 12. Okay, eigenvalues are 3, 3 and 12. Now, the problem, if a problem will be there, it will be because of 3. When you ask 3, 3 says I will not create any problem. I will give 2 eigenvectors. The eigenvectors are given by 0, 1 and 4 and 1, 0 and 4. Then you find them, and lambda is equal to 12. Lambda, you ask lambda is equal to 12. He says I occur only once. If I occur only once, it is my duty that I will give one eigenvector. It gives 1, minus 1, minus 1 and 1. Now, last step is, hence phi is diagonalizable and and basis is and required basis is 014 comma 104 comma -1 and 4. Fine. Next is a numerical in which you do not have diagonalization. So numerical will be of the form, for example, third is phi of x, y, z, in which you say, in this you say that you have x, then you have, let me write it, 1 second, 1 0 1 1 0, then 0 1 0, then 0 0 2, for example. So it will be, this will be of the form, this is x plus y and only y and 2z. Okay, so when you check this, it will be having eigenvalues, it will be having 1 comma 1 and 2, and lambda is equal to 1 will give only one vector, and lambda is equal to 2 will give one vector. But you can feel that you have shortage of one vector, because for R cube, if you want to make basis, you need 3 elements and you have two vectors, but you need one more vector which is not available. So this will be not diagonalizable. I hope this thing is clear to all. Okay,